We've got an important topic about vacuuming and then the present and future by Masa. Let's just settle down and then get started, please. Masa, over to you.
Yeah. Thank you. Can you hear me? Thank you for joining this session. In this session, 25 minutes session, I'm going to talk about the present and future of vacuum in PostgreSQL. And my name is Masahiko Sawada, and I'm a software engineer working for AWS, and I'm also a Postgres major contributor and committer. So let's get started. So for the agenda, I'm going to cover some vacuum basics in the first part of my this talk so that we can be over the same page. And also, I'd like to explain the current vacuum status. I mean, describing the vacuum-related features that are currently available in the PostgreSQL. And in the later half of this presentation, I'd like to introduce some interesting and promising vacuum feature that has discussed in the Postgres community. So before getting into the vacuum details, I'd like to briefly cover how vacuum works today. And I think many of you in this room already know how vacuum works, but vacuum basically consists of the several phases, and phase 1, 2, 3 are main phases. And we always start with phase 1, which is scanning heap phase, and where we not just scanning the heap page, but also doing a hot pruning for each pages, while correcting the dead tuple identifier or dead item ID into a memory storage, so that we can remove the index tuple references to the dead tit later. And thanks to the visibility map, we can optimize the heap scanning. For example, we can scan the all visible page and all frozen page because it's guaranteed there are no dead tuple on these pages. And after that, we enter to the next phase, which is vacuuming index phase, and which is the second phase. And here, the parallel vacuum helps here, speeding up the vacuum. And with the parallel vacuum, the indexes are assigned to the parallel vacuum worker for the simultaneous processing. And after vacuuming all indexes, we go to the third phase, which is vacuuming heap phase, and where we actually mark the dead tit into an unused state so that we can reuse later. And after these three phases, we do the subsequent phases like cleaning up indexes, and truncating heap, and we finally update the heap statistics like a number with tuples and number of pages in the table. This is a basic of how vacuum works. And pgstat progress vacuum view provides important information for the monitoring current vacuum execution and the status of what's going on in vacuum processing. So this view basically reports the current phase and progress in each phase. For example, it shows how many blocks in the table and how many blocks we scanned so far and how many blocks we vacuumed so far in phase 3. And also from the version 17, we have indexes total and indexes processed column. These were new column showing how many indexes on the table and how many indexes we processed so far, we vacuumed so far during the phase 2, actually. And also incoming Postgres 18, we're going to have another one new column called delay time, which shows how much time we delayed due to the cost-based vacuum delay. And so let me introduce some other interesting feature currently available in the PostgreSQL. So the backing to the Postgres version 14, we introduced an interesting feature called Fairsafe Mode, and which is kind of emergency mode that dynamically activates based on the table's age. So table's age represents how old the possible oldest transaction ID in the table is compared to the current latest transaction ID in the system. So Postgres internally uses a 32 unsigned integer for the transaction ID. So the practical transaction age limit is about 2 billion transaction ID age. So Vacuum enters to this Fairsafe mode when table's age reaches 1.6 billion by default. So once it enters to the Fairsafe mode, it gives up the various things and prioritizes phrasing and transaction IDs. Specifically, it stops the cost-based vacuum delay and skips some many phrases such as vacuuming, index vacuuming, and index cleanup, and heap truncation phrases. And it also even stopped using link buffers. So in other words, it's focusing on the phrasing and transaction ID, even if it's meant to use the more resources, because in that situation, it's kind of emergency situation for the whole system. And version 17, we introduced a major update to the how to record the det TID on the memory. And we introduced the new data structure called TStore. And Vacuum now uses the TStore for the det storage. And internally, the det TStore is implemented using by the Redux tree. And our Redux tree implementation is based on the academic paper proposing adaptive Redux tree. So the data structure consists of the key value pairs with the block number as keys and offset bitmap values. So this structure, offers many advantages compared to the flat TID array we used to use Postgres 16 or earlier. For example, it offers to provides a faster TID lookups, which is really helpful for the index vacuuming. And also, with that, we can now allocate the memory incrementally as tree grows. And also, it significantly reduces the memory usage. And we have eliminated the previous 1 GB limitation of the maintenance workmem or Autobacuum workmem. So if you are using the Postgres 16 or earlier and having a vacuum performance issue, I would strongly recommend to update for the Postgres 17 because it's really much faster than previous version and it's very efficient, and we no longer have 1 GB limitation. So let's move on to what's coming next in the Postgres 18. So one of my favorite features in Postgres 18 is eager scanning. So currently, the vacuum has the two types of scans. The first one is the normal vacuum, and which can skip all visible pages and all frozen pages according to the visibility map. And this is the most efficient scan method in order to remove the garbage tuples. And the second type of scan is so-called aggressive vacuum, which can skip only all frozen pages. This means it scans all pages that might have unfrozen tuples in order to reliably update the table's very frozen XID value. Update the table's age. So aggressive vacuum can skip all frozen page, as I mentioned, which is great. But typically, the aggressive vacuum is triggered after table's age reaching 200 million transaction ID age. So that is one problem was that in the situation where we need the aggressive vacuum on the particular table, there are rarely any all frozen pages at that time, and resulting in aggressive vacuum taking a very long time. So eager scanning deals with that situation. With eager scanning, we intentionally scan all visible but not all frozen pages, even during the normal vacuum scan, in order to try to freeze that page, and this ultimately helps increase the number of the all frozen pages in the table. And also, it helps amortize the cost of aggressive vacuum. So since the goal of this eager scan is to amortize aggressive vacuum cost, it doesn't try to freeze all visible but not frozen pages. Instead, it attempts to freeze up to 20% of all visible but not frozen pages. And also it's freezing files. I mean, we eagerly scan the page, but we cannot freeze because of there is some tuples that cannot be frozen at that time. It counts as a fail. And failure count is maintained in the legal region local. I mean, region consists of the 496 blocks, and we reset the failure count for every region. So in other words, for example, if we failed freezing the particular the pages many times in the particular region, we give up the eagerly scan in that region, but we try again in the next region, resetting the failure count. And this utilizes heuristic that different transaction ID generations tend to be located in the different table location. So that's why we reset and we try again the eager scanning, even if we failed many times in a particular the specific area, I mean region of the table. And also in version 18, we can now use the lead stream in all vacuum phases, especially the phase 2, which is index vacuuming phase. We support the lead stream for the B-tree and GIST and SP-GIST indexes, bulk deletion. And also, we're going to have a new vacuum statistics in Postgres 18. New columns like such as total vacuum time, auto vacuum time, and total analysis time, and total auto analysis time are introduced into the Postgres PG stat all tables. And also, as I mentioned before, the PG stat progress vacuum view will going to show the vacuum delay time as well. So let's now move on to the last part. So from this part, I'd like to introduce some promising and interesting features that I have discussed in the PostgreSQL community. But please note that I cannot promise that these features are going to be committed in the future because these are totally under discussion. And maybe it's quite possible that we introduce this feature with some major design changes, or even we reject it based on the discussion. And also, I included the discussion links in each slide. So if you're interested in some features, please comment and review the patches. So first one is a parallel vacuum. I mean, we already support the parallel vacuum, but it's only for the phase 2. But the idea here is to support more parallelization in phase 1 and possibly phase 3. There, I think, there are some possible promising use cases. For example, one is vacuuming a table with no indexes, because such a table cannot benefit from the parallel vacuum today. And also, I think the parallel vacuum is very suitable for the freezing the entire table, and especially in the emergency situation. So I think my plan is to integrate the parallel vacuum with Fairsafe Mode, I think, which is very makes sense. And looking at the graph on the left side for this slide, this shows execution time of with parallel vacuum and without parallel vacuum. The left 3 bars, a red, orange, yellow graph shows the current PostgreSQL, I mean without parallel vacuum. And right side, green, blue graph shows with the execution time with the parallel vacuum. And each bar is stacked bar and showing the execution time for each phase is 1, 2, 3 from bottom to top. So looking at phase 1 execution time, phase 1 time on the left side, I mean yellow graph, even if we increase the periodically from 1, 3, and 6, it doesn't change. But with it changes, only the phase 2, the speed up. On the other hand, looking at the right side, as you can see, if we if I increase the periodically 1, 3, and 6, it reduces the phase 1 execution time. And a second interesting feature the proposed Postgres community is the more statistics. So we already have some statistics like about the table, for example, number of indexes, number of dead tuples, but the idea is to store the correct more statistics related to the vacuum. So the patch tried to introduce some new views, such as pgstat vacuum tables, indexes, databases, and for example, the pgstat vacuum tables shows something like that. This is output I just tried last week. So the proposal patch tried to introduce the many statistics, and I think everything is almost every statistics that we correct in the view is the same as that we have in the vacuum bubbles command. To be honest, I'm not sure that all statistics are really important, but maybe having more statistics will be very helpful for tuning the Autobacuum behavior and for the future. So maybe we can discuss which statistics is really required and move forward this project. Yeah, actually, we had a good discussion yesterday at the patch advanced feedback with the author, and I hope we can move this project forward. And another interesting one is Repo Command. And this is kind of similar to the cluster and vacuum for command because it basically rewrites the table in order to shrink the table size. But we are trying to introduce a new command. So unlike cluster, the Repo command doesn't require any index to operate. And also, unlike cluster and vacuum full, it's going to support concurrently option, which is great because we can accept the read and write on the table while rewriting the table. So as for the concurrently option, it employs the basic implementation of PG squeeze approach. And I mean, it internally uses logical decoding in order to capture the concurrent writes happen during the table rewrites. And also, even if you are using the replicable level, it also enabled the logical decoding. I mean, transparently increase wall level temporarily in order to use the logical decoding for that specific table. This is very smart. And also, this is another interesting feature that we discussed a couple years ago. Currently, vacuum executes all phases as a single operation. But the proposed idea is to decouple vacuum, table vacuum, and index vacuums. So this is because the table and indexes have different optimal timing requirements. For example, B-tree index has bottom-up duration optimization. And it may work very much better for some indexes than others. So meaning that we could have some indexes that badly need to be vacuumed because they are full of garbage, and other indexes on the same table where bottom-up duration work perfectly, and there is no need to vacuuming at all. So core concept of this idea is to record the date in a new fork called dead fork, instead of having such dead information only on memory. We can serialize this. The idea is to serialize these dead information to the disk so that we can use later. So with this feature, I think we can do for example, doing heap pruning multiple times on the table while correcting a dead into this fork, and without invoking any index vacuuming on some indexes that don't actually need to be vacuumed. And then once it really needs to be vacuumed, we can only invoke the vacuum index vacuuming phrase on that particular indexes. Also, this could be a key feature for implementing global indexes. We don't have global indexes yet, but assuming the partition table where each partition has a local index, and there is also a global index, which indexes tuples from every partition. If we try to vacuum such a partition table in a naive way, probably we would end up having to vacuum the global index every time we vacuum any partition, which fairly expensive. So with this feature, we can do like vacuuming only partition and its local index and multiple times. And then after that, when we really necessary to vacuum the global index, we can invoke only index vacuuming on the particular global indexes. So development seems to suspend it a few years ago, but I think it's a very promising feature. And there are some proposals regarding the auto vacuums. And one is to use using a parallel vacuum on the auto vacuum. So as you know, currently parallel vacuum is only available in manual vacuum, vacuum command, but the idea is to use parallel vacuum also on the auto vacuum. So at a glance, the purpose seems to be conflicted because parallel vacuum is meant to vacuum, speed up the vacuum while using more resources, whereas auto vacuum is designed to vacuum on the table with the minimal impact on the foreground transaction processing. But I see there are the potential use cases, and for example, the vacuuming on the table, large table with many indexes where auto vacuum struggles to keep up. I think in that case, it makes sense to use the speed up the auto vacuum even if we use more resources. And also, as I mentioned before, I think once we have a parallel heap vacuum, which would be suitable for the Fairsafe mode. Also, another idea proposed related to the Autobacuum scheduling, which is really interesting. And currently, Autobacuum triggers based solely on the dead tuple count, so number of the dead tuple on the table. However, having many dead tuple doesn't guarantee they can be removed, right? For instance, right after many dead tuples are created, if replication slot or prepared transaction or long line transaction holds the older X-min, we might not able to be removed any dead tuples. So this idea is to address this kind of issue mentioned as useless vacuum, mentioned in the Robert presentation last year. So the idea is maintaining the histogram in order to track when the tuple was created in terms of a transaction ID. So with that, we can estimate how many dead tuples we might be able to remove if we run vacuum this time. I think it's very interesting feature. The last time I checked the thread, last week, that thread doesn't get any reply. But after this conference, I'm sure I'm going to review that and study more. And yeah, I like this idea. So to wrap up, I briefly introduced some interesting and promising features, and maybe what we possibly have in the future Postgres. And so at the end of the presentation, the one question I'd like to ask all of you in this room is, what aspects of vacuum we can improve further, given its significant improvement recent years? So I think one of the key area we need to improve is Autobacuum scheduling optimization. Autobacuum itself is now very faster, got faster, but the many systems still relies on the Autobacuum. So maybe optimizing more Autobacuum scheduling is a key area we can improve. But yeah, I'm very welcome any ideas and feedback, and I would love to hear some experience and problems the user actually facing. So all this input will help generate the solution and lead to improvement in the future vacuum. So yeah, that's all for my presentation. Thank you for listening.